So hello everyone. Thank you first of all for the chance to give this talk today. So as said, I'm Jana Ochs and I'm a PhD student in the group of Eva Weig who cannot be here today. And so in the next 40 minutes, I'm going to tell you a bit about the spectral evidence of squeezing in a driven nonlinear nanomechanical resonator. And I think with that, I'm going to change topics again quite a bit. So this is about the nonlinear dynamics of a nanomechanical resonator completely in the classical regime. So therefore, I want to first tell you a bit about this nanomechanical resonator. So in our case, a silicon nitride spring resonator, and also how we can drive and control it. And afterwards, very important for the measurements I'm going to show you is the characterization in the linear and in the nonlinear regime. Where in the nonlinear regime, we're going to conduct all our measurements. So the second part and the third part will then be about two of our recent results, both about the squeezing of thermomechanical fluctuations. And therefore, I want to present you two measurement methods. So first one in the power spectrum and the second one with a two-tone spectroscopy. Okay, so how can you imagine our nanomechanical resonator? So for that, I would like to start with this beautiful picture of a nanoscale guitar made by Carr and Craighead in 1997 at the Cornell Nanofabrication Facility. So I think it really nicely represents what our nanomechanical resonator looks like. So basically, they're just tiny guitar strings. And an SEM picture of our particular resonator is shown here in the middle. So it is a long and thin string made of highly pre-stressed amorphous silicon nitride that is suspended between these two clamping pads. And the typical dimensions are given here. So it has a length of 50 micrometers and a cross section of 200 times 100 nanometers. So if you want to get a number for the eigenfrequency of this nanomechanical resonator, you could use the string model. So here the eigenfrequency omega naught is a function of the mode number n, the length of the string L, and the square root containing the material parameters stress and density. So for the fundamental out-of-plane mode of our resonator, so out-of-plane mode means the string is moving up and down as it is shown in the sketch here, we find an eigenfrequency of 6.5 megahertz. And this mode is also the only one we're going to look at throughout my complete talk. So now you may ask the question, why is it interesting to study these nanomechanical resonators? So this is because of a broad range of practical applications. So this is all going into the direction of sensing. And the bottom line here is that these nanomechanical resonators are so tiny that they are basically sensitive to everything what is going on in their environment. And the example I picked here is about mass sensing. So the idea is that this nanomechanical resonator is so small that even if an atom is absorbed, the change in the resonance frequency is measurable. And in this particular example I have chosen here, the authors have shown that they could even reach a yoctogram sensitivity. So for comparison, a yoctogram corresponds to the mass of a proton. But these nanomechanical resonators are, of course, also very interesting in terms of fundamental experiments. So for example, to investigate nonlinear dynamics. So therefore, these nanomechanical resonators are prime candidates because it is relatively easy to drive them into the nonlinear regime. And people have learned how to control these resonators in almost all degrees of freedom. So it is possible to investigate all these plenty nonlinear phenomena. For example, in the work I picked here, it's about the bifurcations. So bifurcation is a point where the number of stable solution is changing. And with that, so looking again to the left-hand side of this slide, you could build, for example, a bifurcation-based amplifier. So in the light of this workshop, I should not miss to mention that it is also possible to operate these nanomechanical resonators in the quantum domain. So in the work from 2010, it was shown that it is feasible to attain quantum control of single mechanical quanta in a nanomechanical resonator. So the one depicted here. And with that, the research field of quantum nanomechanics got started. But as said, everything what is going to follow is in the classical regime. So how can we control our nanomechanical resonator? So typically one picks an electrical scheme and the resonator gets metallized. However, this metallization introduces a lot of losses at room temperature, where we, for example, want to investigate our resonator. So we need to do something else. And the scheme we are using is shown here in an artist representation. So what do you see? Imagine you're sitting here at one of these clamping pads and you look down this long and thin string until you see in the end the second clamping pad. And now you can see that to the right and to the left-hand side of this string resonator, we have two gold electrodes. And now you can imagine if we apply an electrical field between these two electrodes, the string will sense this electrical field. But now these two electrodes are not placed symmetrically along the string, but with a tiny offset, such that the electrical field which is generated is inhomogeneous. So this is indicated by these field lines here. And with that scheme, we can now do a lot of things. So first of all, you see here another SEM picture of our resonator. So the string here colored in green, you have here the two clamping pads, and the string is flanked by these two gold electrodes colored in yellow. So the sample is placed in the vacuum chamber and everything is operated at room temperature. So first of all, we want to read off the motion of this resonator. And for that, we can use the two electrodes. So these two electrodes basically form a capacitor. And now as the string is moving in and out of these two electrodes, the capacitance gets periodically modulated. Of course, this is a small modulation and one will need some electrical tricks to retain the mechanical signal. This can be conveniently done by a microwave cavity operated as well at room temperature. So this microwave cavity is connected to one of these electrodes with a bond wire. And now as the capacitance get modulated, the eigenfrequency of this microwave cavity gets modulated. And now if we pump this cavity on resonance, we will get two sidebands in the cavity signals. And these two sidebands, they contain the mechanical response. And now with the help of an in-phase and quadrature mixer, we can extract the mechanical signal, which is then captured by a measurement device. And this scheme is typically enough to resolve the thermal motion of our string resonator. On the other hand, we can use the inhomogeneous field which is generated to actuate our resonator, so to drive it. So what happens if we expose a dielectric string into an inhomogeneous field? So what will happen is the following. So this dielectric material is polarized. So little dipole moments are building up, and these dipoles are attracted to where the electrical field is strongest, which means they are basically pulled towards the electrodes. And now you can imagine adding to this DC bias a periodic driving force. So the periodic drive will act on the dipoles and therefore actuate our resonator. So with this integrated scheme, we can drive and detect the motion of our resonator. But it turns out that the DC voltage has another beneficial effect. So the DC voltage actually sets the equilibrium position of our string resonator. So depending on the DC voltage, the string will experience a different electrical field gradient. And now this field gradient is actually nothing else than an additional spring constant. So if we can change the spring constant, we can tune the eigenfrequency of our mode. And how this looks in real is plotted here. So here we can change the DC voltage, and you can see that we can tune the eigenfrequency of our mode in a parabolic way. So this dielectric gradient field transduction is very helpful if we want to control our resonator, so we can drive it, we can detect it, and we can also tune the eigenfrequency of our mode. So with that, we are ready to do the first measurements. And the first thing we normally do is the characterization in the linear regime. So for that, we apply a relatively weak driving voltage and we measure the frequency response. So we sweep the frequency through the resonance and we measure the amplitude response. And what we get is this nice symmetric response curve. It turns out that the response of our resonator can be modeled by the damped and driven harmonic resonator, which equation of motion is shown here. So we have the coordinate Q, we have the damping parameter gamma, we have the restoring force, and the driving term. So in our case, we always apply the drive on or near resonant. So by solving this equation for the amplitude, we can get the susceptibility, and this susceptibility is used to fit this amplitude response. And from that fit, we can then obtain the parameters we need to characterize a resonator. So this is the eigenfrequency. So here 6.5 megahertz, and the damping or the line width of our resonance, which is 20 hertz. And from these two quantities, we can then define the third important quantity. So this is the mechanical quality factor. And this is in our case above 300,000, which is quite remarkable for a room temperature device. And as it turns out, this high mechanical Q factor is crucial for the measurement I want to show you in a few minutes. Okay, I told you this is going to be nonlinear dynamics, so we have to drive a resonator in the nonlinear regime. And this we can do by increasing the drive voltage. So here I plotted again the linear response. So here you have the frequency and the amplitude. And now if we start to increase the drive, you can see that the amplitude is increasing, but also that the amplitude tips over and gets asymmetric. So, and now as we sweep in both directions, so sweeping up and sweeping down, we can also see that the response is getting hysteretic. So obviously we have to extend the harmonic approximation. And the simplest model accountable for that is the Duffing model, which essentially is the harmonic resonator plus this cubic nonlinearity term. And for all I'm going to present, we can stick with this model. So we don't need any other nonlinearities. So the Duffing nonlinearity gamma comes with the amplitude cubed. So therefore, it is crucial to have a high Q, which allows our resonator to reach amplitudes large enough to enter this nonlinear regime. On the other hand, this cubic term tells us that we can have up to 3 amplitude solutions. And if we fit our response to the Duffing model, we can actually see those. So we have here the first one colored in red. This we call the high amplitude solution. And we have the one down here, which we call the low amplitude solution. And then there is a third one, the orange branch here, which is an unstable solution. And unstable in our case means that we have no data points here. Now we can look at 2 interesting points, which I labeled here by these crosses. So these points are the bifurcation points. So here the number of stable solutions changes from 1 to 3 solutions and then back to 1 solution. And within these 2 bifurcation points, we have the region of bistability, which is here in the blue shaded region. And here you can now nicely see that in this region, our resonator can have 3 possible solutions, where 2 of them are stable. From the Duffing fit, we can now also obtain the value of the Duffing constant gamma, which in our case is positive. And this Duffing constant, you can think of it like an additional spring constant. And as the spring constant is positive, our resonator is getting basically stiffer. And if the resonator is getting stiffer, we increase the eigenfrequency. And this is the explanation why the curve, so the nonlinear response, bends in our case to larger frequencies. So from a theoretical perspective, this Duffing resonator is best treated in the rotating frame. So what I sketched here is the lab frame. And what we look at is the response of a driven resonator. So here we have the phase space, so with coordinate and momentum. And if we have a driven resonator, this will follow this closed orbit at the frequency, at the drive frequency omega f. But now you can imagine switching from this lab frame to the so-called rotating frame. And this frame is now just rotating at the drive frequency, which means in this representation, the resonator is basically in rest, and we can draw it as a fixed point. Of course, you have to change your coordinates accordingly. And now in the rotating wave approximation, the dynamics of these 2 new variables here can be described by a Hamiltonian function. So here, h of the two coordinates. And this Hamiltonian function is plotted here for the Duffing resonator, so in the bistable regime, here in a 3D image, and below the corresponding 2D plot. And from this phase space landscape, you can now see again these two stable solutions, which we have seen in Duffing resonator. So we have two fixed points. One here, the minima, which corresponds to the high amplitude solution, and the second one, which is the maxima here, which corresponds to the low amplitude solution. So the third branch, the unstable solution, would correspond to a saddle point, which is somewhere here. Okay, with that, I would like to come to the second part of my talk, so the squeezing of thermomechanical fluctuations. And of course, for that, we have to add the thermal fluctuations, which we have in our system. So I told you, we are operating everything at room temperature, so we will have some thermal fluctuations. So here I added them to the equation of motion. We also have the Duffing term here, so all what is going to follow is in the Duffing regime. So we always apply a strong drive, and what we will get, we can again explain by this phase space landscape, where we can then see these two stable fixed points, the high and the low amplitude solution. So what now happens if we add this thermal noise? So it turns out that due to the thermal noise, the system will not stick to one of these two stable states, but it is being kicked out of it. So we will start to meander around the stable state as indicated by the wiggling lines. And now you can imagine this high amplitude solution in the phase space. It's kind of a bowl, and the thermal noise will sample this potential bowl. Now in the rotating frame, this thermal fluctuation can be described by a harmonic resonator, which frequency is governed by the curvature of the potential landscape here. So the curvature along the x1 and along the x2 quadrature. And this additional frequency is a very small frequency. So for our resonator, it's in the regime of like 100, 200 hertz. So what happens now with this additional small frequency we have in the rotating frame if we go back to the lab frame? So you can think of it like a mixing process. So this additional weak frequency, this very slow frequency, will mix with the strong drive into two satellite peaks. And these two satellite peaks appear at the drive frequency plus and minus this additional slow frequency. And these satellite frequency correspond to these thermal noise-induced small amplitude vibration about the stable state of our driven resonator. So these satellites have already been weakly observed in an experiment from Ho-Boon Chan's group after the injection of additional white noise. And the plot you can see here is taken from that paper here. So you have here the strong drive, and you can guess right and left to this strong drive peak these two satellites. Now in our case, because we have this very large mechanical Q factor, the picture is much, much clearer. So what do you see here? So we look at the out-of-plane mode of our resonator, and we drive it to the nonlinear regime. So we apply a strong sinusoidal drive tone directly on resonance. And then we measure a series of power spectra for different drive powers. So here you have the frequency, which is rescaled, so it's the detuning, so 0 corresponds to drive on resonance. And here you have the drive. And now here centered at 0, you can see the central bright line. This corresponds to the driven response of our resonator. And right and left to this central line, you can now see these two satellite peaks, which are spaced symmetrically and with a power increasing spacing. As we know the satellite frequency, we can now compare it to the theoretical model, which is shown here by these red open circles. And as you can see, we find a very good agreement. So please note that this is only theory, so no fit, no free parameters. This is what we get upon careful characterization of our resonator. We can even better see the satellites if we look at the line scan here at minus 20 dBm. And from that you can see, so we have truncated the drive tone here to make the satellites a bit better visible. And what you can see is that these satellites have a very nice Lorentzian line shape. And the line width is the same as we have found for a resonator in the linear regime, so 20 Hertz. The striking observation here is that one of these satellites is much, much brighter than the other one. And to explain you how that comes about, I would like to go back to the simplistic picture of a driven resonator in the rotating frame. As I told you, this can be reduced to a fixed point. But the fact that I didn't draw a point, but this elongated blob, reflects again the fact that we have thermal noise in our system. So the spread of this blob should correspond to the temperature. So this is given by the equipartition theorem. And the equipartition theorem also states that the elongation, so the distribution of the noise, should be the same in both quadrature components. And if you would imagine that again, like in the space-based landscape, this would mean that the curvature in this potential bowl is the same for the x1 and for the x2 quadrature component. But now if you look back at this phase-based plot we have found for our Duffing resonator, you can already tell that this cannot be the case anymore. So if you look here at the high amplitude solution, you can see that this potential bowl is not circular. It is stretched out. It is more something elliptic. So this means that instead of a circle, we end up with this ellipse here. So we have a squeezing effect, which means that the distribution of this noise cloud is not the same in both quadratures. And as visible in this plot, the curvature along x1 and x2 is not the same anymore. And what is happening here is the following. So due to the strong periodic drive we add to our system, we break the time reversal symmetry, and this leads to the squeezing of the thermomechanical fluctuations in our system. So squeezing by itself is nothing new, and we have heard about it quite a lot within this workshop. And you all know that the origin of squeezing is in the quantum regime. So the example I picked here was the first observation of squeezing already in 1985. But squeezing is not restricted to the quantum domain. You can also have it in the classical domain, with the difference of not squeezing quantum fluctuation, but thermomechanical fluctuations. And this has been first observed with microwave radiation in a Josephson parametric amplifier, but also a bit more recent in a nanomechanical Duffing resonator under the additional white noise injection. So all these measurements, so if you want to measure a squeeze state, are typically done with a homodyne detection. But it turns out that this very standard procedure can get very tricky if you have some small frequency fluctuations in your system. And to explain you why, I'm using this very nice paper from Hong Tan's group. So they tried to measure the thermomechanical fluctuations of a resonator for different temperatures. And they can very nicely see the equipartition theorem. So if they increase the temperature, the circular distribution of the noise is increasing. So blue is for relatively small temperature, and if they are at room temperature, this plot is increasing by quite a lot. They can now also measure the response if they sweep through resonance. So if they want to sweep through the Lorentzian response. And what they get is this circle here. But now if they want to drive at a particular frequency, so for example here on resonance, and they try to map out the noise again, they end up with these elongated banana shapes. So there is something which is messing up the data. And how that comes about, I would like to show you this theoretical plot of the two quadrature component. So the black line is the in-phase quadrature, and the gray dashed line is the quadrature component. And as you can see here on resonance, the in-phase component has a very, very steep slope. So if we end up to have some tiny frequency fluctuation, which are mostly just unavoidable in this system, you will get a big, big spread in the in-phase component. And this is exactly what is measured here. So it turns out that doing these homodyne measurements in the presence of small frequency fluctuation can be very, very tricky or almost impossible. But as long as these small frequency fluctuations are small, they only negligibly distort the spectral peaks I have just shown you. And it turns out that by looking at these spectral peaks, we can actually obtain the squeezing parameter completely without the need of doing this homodyne detection. So how does this work? So from the theoretical model, it comes out that the area ratio, so I plus is the brighter satellite and I minus is the weaker satellite. So the ratio of these areas is directly connected to the squeezing parameter phi. So the only thing we need to do is to extract the area of these satellites, which can be easily done by Lorentzian fits. So here the green data is the extracted area from that satellite as a function of the drive power we measured here, and the same for the weakest satellite here colored in blue. And you can see that there's actually quite a big difference in the enclosed satellite area. The red line is again our theoretical model, and again we have a very good agreement. So from these areas, it is now easy to calculate this ratio. So this is shown here. Again, the black dots is our data and the red line is our theoretical model. And with that, we have just by using these spectral peaks, we have determined the squeezing parameter in our system without the need of doing a homodyne measurement. So as a last step, we can now convert this squeezing parameter to the more usual seen plot. So we can reconvert it into these mean square fluctuation, which are given here by these two relations. And here you can see if the squeezing parameter is 0, so if we would not drive our system, we would come back to the simple equipartition theorem, which is plotted here as the circular distribution. So with that, we can calculate this line here. So these are the thermal fluctuation present at our lab temperature. And now you can see if we use this conversion, we can see that the in-phase component is squeezed by quite a lot below the thermomechanical limit at the expense of enlarging the fluctuations in the other component. So with that, we have clearly shown that we can squeeze the thermal fluctuations in this present of a strong drive. So if we drive a resonator to the Duffing regime. Okay, so I have promised you to tell you about a second measurement technique, and this is the two-tone spectroscopy. So here, instead of using a single drive and doing a power spectral measurements, we want to use two drive tones. And this can be done with the help of a lock-in amplifier with a multi-frequency option. So we can output a strong RF drive tone, which we directly apply on resonance, and then we can use a second weak probe tone to scan across the resonance. And we basically do the same as before. So we measure a lot of these response curves for a variety of different drive voltages, and we plot them in this nice map here. You can see again on resonance, we have this very big feature. So this is the response to the drive, and to the right and to the left of this drive tone, we have the two satellites. Now you may say, okay, this looks a bit different than before, but this is just because now we plot the data here on a linear drive voltage scale. If you look again at the line scan here at 50 millivolts, we can nicely see these two satellites. So we have again a brighter one and a very weak one. So in this case, the explanation is a bit different. So here the satellites are now not thermal noise induced, but they're induced by the second weak probe tone. But the theoretical model stays exactly the same, as this weak probe tone also has the same effect than the thermal noise. It kicks out our system out of the stable state and it will start to fluctuate around. And these additional fluctuations will mix back into these two satellite peaks. So we can use the same model as before to describe the position of the satellites. And you can see we find again a very, very nice agreement. So these probe-induced satellites have already been observed in the group of Antoine Heitmann. So you can see here the strong drive and the two satellites, which are very well resolved. But they didn't do the comparison or the connection to the squeezing, which I want now to come back again. So by doing this response measurement, one can basically look at two quantities. So we can look at the susceptibility, so the amplitude response, which is plotted here, or we look at the absorption of the probe field, which is the imaginary part of the susceptibility. So in both cases, at resonance, we see the very big feature, so the response to the drive, and we see a big satellite and a very weak one. But now here's something interesting is happening. So the weaker satellite actually appears as a dip and not as a peak. And since this measurement gives us the absorption of the probe field, this actually corresponds to the amplification of the probe field. So we are pumping essentially energy from our resonator in the probe field. And this we find very interesting, and we want to investigate this a bit more. But let me come back to the squeezing. So similar to before, the squeezing parameter is encoded in the satellite area ratio. So we can again extract the area and can calculate the squeezing parameter, both for the response spectra, but also for this quadrature component, so for the imaginary part. And it turns out that the satellites here have again a Lorentzian line shape with the same line width as we have seen before. So we can again calculate this ratio, which is plotted here as these black dots, again as a function of the drive voltage. Red is again the theoretical model, and you can see this is again nicely in agreement. And you can see that the squeezing parameter is basically independent on the drive voltage. And if we calculate the squeezing parameter, we find a value here 0.28, which is very close to the one we obtained with the theoretical model, which is 0.27. Again, as before, we can also re-express this squeezing parameter in terms of the mean square fluctuations. And we see again that we can squeeze the in-phase component in the presence of strong drive below this thermomechanical limit for our room temperature experiment. Okay, so why do we now do the second measurement? So what's special about that? So it turns out that as long as we are in the classical regime, these two methods are basically the same. So in both cases, we can very nicely resolve the sidebands. And in both cases, they show the unequal intensity. So we have a brighter one and a weaker one. And with that, we can characterize the classical squeezing in our system without the need of doing a homodyne detection. But if we now would like to do the same in the quantum regime, it turns out that for the measurement in the power spectrum, we would still see sidebands, but they would have equal intensity. So we could not extract the squeezing parameter here, even though we would have the squeezing here, in this case of quantum mechanical fluctuations. But on the other hand, now the nice point about these two-tone spectroscopy is that in that case, we will still have this unequal sideband. So even in the quantum regime, it should be possible to obtain the squeezing parameter out of this spectral method. And we would be very much looking forward if someone were able to do this experiment and show the data here. Okay, with that, I'm coming towards the end of my talk. So in the first part, I was telling you about the nanomechanics of our Duffing resonator. And I hope I convinced you that these nanomechanical resonators are very nice candidates to look at the nonlinear dynamics. And for example, I showed you these two recent publications from us, so where we looked at the evidence of squeezing, so first in the power spectrum, but also in the response spectrum. In both cases, we have these well-resolved satellite peaks, and it turns out that we can easily extract the satellite area and with that the squeezing parameter. And the beneficial point of the second method here is that this would be also equally applicable in the quantum regime. And I don't want to finish without thanking my group and collaborators, so especially Eva Weig, my supervisor, Maximilian Seidner and Johannes Kolbe, two former students working on the project, and also many thanks to our theoretical support, so from Gianluca Rastelli from the University in Trento, Mark Dickman from the MSU in Michigan, and Wolfgang Belzig from the University in Konstanz. And also thank you for your attention and I'm happy to answer your questions.